So from bag houses to precipitators, and mine's a little different to Tim's, but my name is Paul Ford. My company is Redkoh Industries. We're actually a controls company. We build controls and electrical systems for precipitators. So we're pretty much a sub-supplier to most of the people that you might deal with. We're a fairly advanced company. Just want to go ahead and change that. We've been in business for 30-odd years. We're based in New Jersey, and I had a quick look at the list of attendees, and for the most part, people at TVA will be using our equipment, but badged through American Air Filters, AAF, who are one of our bigger OEM customers. East Kentucky's the same. Again, AAF use our stuff at their East Kentucky plants. And on some of the Dynegy plants, I believe that we are badged with Environmental Elements name. So you can see that the Redkoh name itself is probably not that well known, but we sell an awful lot of controls to precipitator OEMs, and these get spread throughout the world, and it doesn't take too long to have a fairly large installed base. This gives an idea of roughly where we have systems. So today, my 20 seconds and 2 minutes worth of knowledge is to do with what appears to be becoming a fairly significant problem in the power generation industry, and that's one of boiler load cycling. I am an electrical engineer, so I don't really purport to know a great deal about the chemistry of corrosion and acid gases and such like. But unfortunately, being part of the precipitator means that we get stuck with anything that comes our way. And I have the unfortunate experience of going through far more precipitator startups and shutdowns than I would actually want to or enjoy or even like. So in the pursuit of what load cycling means to us all, when it comes from a precipitator perspective, really it seems to me that what we're looking at is just startups and shutdowns. Continual startups and shutdowns. And there was a time where people started up a precipitator and it ran for months and months and months. And then we shut it down. And when it was down, we worked on them. And after the work was complete, we went through a startup and went back into that same process. But this whole concept of literally cycling in very short time order is to me nothing but trouble. Absolutely nothing but trouble. It just raises the risk of how we run our systems by such a substantial amount that it gets very difficult to pinpoint what we might do to enhance the performance of our precipitators with the tools that we have. And I've done a lot of reading and I've done a lot of work on plants, and I very rarely go to a plant where they have what might be called an exemplary startup. So that, what does that mean? Well, it means you fire on oil, you fire on gas, you move things along, the temperatures rise quite nicely. Depending on where you are in the legislation, the fans come on, you energize the transformer rectifiers, the emissions are low, and you slowly climb to full load. The temperatures rise nicely, you don't have mills dropping in and out, and it smoothly gets up to full load and everybody's happy. Now, there might be a place where this happens, but it's not been my experience. Almost every startup that I get to experience is one where something goes wrong, and we have a situation where something in the process comes back and hits us from behind. This once a year or once every however long process is now turned into a weekly, daily, whatever your cycle of operations is. So I can see that it really has become an issue. Further to that, looking at the issues that we're faced with when we go through the slow cycling, these low cycling startups, and looking at what we have, almost no two startups or no two plants go through exactly the same set of scenarios on each occasion. So just really picking out the one that's most pertinent to what we're concerned with when it comes to precipitators and precipitator controls. Temperature is probably by far and away the fundamental behind anything that happens. Temperature changes basically manifest themselves in a number of different ways throughout the plant. And the biggest one that I feel is worth mentioning is that of thermal transfer. Now, boiler operation, boiler operators, boiler control systems people, boiler manufacturers are totally familiar with this concept, because the fundamental behind getting heat through to the tubes is keeping the tubes clean. Hence the reason for soot blowing. So when you find that you're not getting thermal conductivity from the fires through to the tubes, you go into a process, you clean the tubes. So you get a better thermally conductive set of circumstances. Now, you take that back to the precipitator, it actually works in very much the same way. Once we start to experience a buildup of ash on the surfaces in the precipitator, that ash actually presents a reduction in the steel's ability to, first of all, rise to temperature and subsequently fall from temperature. So in load cycling, one of the things that is pretty much the most interesting thing is the consideration of the fact that there is a significant time lag between the time that you generate the heat up at the front end and the time that the materials in the precipitator get to temperature. In an ideal world, we would hope that that temperature rise curve occurs once in a cycle. So we start up from cold, the temperature of the gas rises, we go through the acid dew point, we stay above the acid dew point, and the sheet metal of the precipitator rises, gets to the same temperature as the gas, and we're out of the area of concern, which is one where we find condensation of moisture and acid gases on the plates, all with the same reasons that have been mentioned earlier. As soon as you have condensation of acid gases, we're into an area of corrosion and things that I don't understand. However, my visual inspections show me that once things start to corrode, the other issues that come along with precipitators, which are wrapping, high voltage, cause the precipitator to deteriorate from a mechanical perspective. So we start to get erosion, spark erosion, we start to wrap, and we find that the outer surfaces of the plates, which are corroded, tend to fall off, and all of this creates a problem in the actual performance of the precipitator. So the fundamental of thermal transfer, acid dew point are absolutely critical when it comes to getting a decent startup. So this cycling process leaves from a controls perspective, there's not a lot we can do to support keeping this whole mechanical equipment put together over the long term. It's very much out of our hands. What we can do is to support the mechanism whereby you get a reasonably clean startup. But it's very much a team effort. It's not from the back end, and it's not specifically from the front end. So we have to go through the tools that we have at our perspective, which are wrapping strategies, power set, TR power delivery, working with operators, design enhancements and plant enhancements to make this whole concept of cycling reasonably successful and to reduce the amount of risk that's involved with it. Okay, next. So, in an effort to provide some guidance, I put a few points together, fundamentally around the fact that a cycle from low load through to full load and back to low load again is nothing more than a startup and subsequently a shutdown and then some idle time. And often it comes from people who have to work with not only the control systems but the boiler operators. Well, what should we do? Which is the best way forward? How should we start our precipitator up? And once you put your heads together with the operations people, you can establish some degree of sensible strategy. But it's not going to be the same across every single plant. It comes from experience, working together, and determining what the best way forward is. Even as control systems engineers, we can't really agree among ourselves which might be the better way forward. So a lot of this you need to take with a pinch of salt and try it in both directions. Bearing in mind that if you were to put some sort of temperature measuring equipment on the plates inside your precipitator and try and monitor the rate of steel temperature rise versus the rate at which the gas temperature rises, then when you have that relationship, you can possibly determine whether it might be the best thing to do to start a precipitator up when you energize fields from the front of the precipitator towards the back of the precipitator, or from the back of the precipitator to the front, or from the middle out. And there's things to be said in almost all of those scenarios that would benefit or might be of a non-beneficial nature. I like to use these few points over here in this fashion when I start a precipitator from cold. I always like to consider the fact that with the status quo being the entire precipitator, all the steel is at the same temperature, I want to try and keep the dust off the plates. So when we start and we put in the fires, mills come in. Nowadays we're stuck with fan on, precipitator on. There's almost nobody that's allowed to not do that anymore. In the old days when I was an intern, we used to sort of stand with our backs up against the control panels and prevent anybody from turning them on until we saw decent temperatures, but those days are gone now. But the loophole still exists that you don't have to have the entire precipitator turned on. Fan on, precipitator on is very much something that you could negotiate. But the point being is, just like on the tube situation, if you can keep the sheet metal as clean as possible during those early hours of first fire, the thermal conductivity issues surrounding ash layer on plates is far less of a problem than it might be. So if you can keep the plates clean whilst you're raising the temperature, you're going to get that temperature from the gas into the steel faster. If something goes wrong and you plug up the plates or gum them up, what's going to happen is that bit of material that's now layered on the plates is a thermal barrier. You can put aside the fact that it's also an electrical barrier, because that's a huge problem too, because now you've created not only a thermal problem in that you can't get the temperature into it, but you've now got a process barrier in that you can't produce the current that you need to collect any further. So the first point over here, if we can try and limit the amount of buildup on the plates, it's a scenario, it's not the perfect one, but bottom line is beat hell out of the plates in those early few hours. There will be re-entrainment. However, hopefully you're at a relatively low firing rate, You will have slightly higher moisture contents. The temperatures are not up there. The moisture has a tendency to fall out. You will have relatively low resistivity issues because of that additional moisture, and you will have agglomeration. So putting all that together, there's likely to be some decent fallout purely by gas velocity particle mass. So even though you're wrapping and stuff is not sticking solidly to the plates, hopefully it's falling due to those other characteristics that I've just mentioned. And energize the fields. Only energize the fields that you need to maintain the minimum opacity, or at least stay below your limits. It's not a perfect scenario. There's always the argument, should it be the front, should it be the back? But just consider this as a possibility. In the early stages of startup, the temperature in the precipitator rises from front to back. So if you do gum something up, where would you like to gum up? And in my opinion, I'd like to gum the inlet up. Because gumming the inlet up is also the place that is most likely to clean the soonest after the startup is through. That's where the temperatures will be highest. The stuff will burn off the plates. It will fall off. The particulate size that's collected up at the front of the precipitator is also the largest. There will be scouring effects. So the front field, added to the fact that the front field on any precipitator is typically wrapped far more frequently than any of the other fields, the front field will clean up the fastest. So that's my opinion. But, as I say, there's plenty of people out there that do it from the back to the front. And I think it's a plant by plant, and it's your experience that ultimately will determine the right way to do it. The backfield's polish, but when you only wrap a backfield once every 30 minutes, or on some of these bigger plants, and I'll take you to India, once every 18 hours at the back of the precipitator, it takes an awful long time to clean a gummed up field at the back of the precip. So that covers the first two lines. So delay starting up all the TR sets for as long as you can possibly get away with. Get that temperature in there. Keep an aggressive wrapping system until you get to the point where you absolutely know you have to have an optimum wrapping strategy to maintain a full load situation. And I think it's fair to say that it's really the last 10% of the megawatts that you're trying to produce is where the problems start to happen. You know, you can ramp up without any issues and emissions are maintained and everything's looking good, but you get that last little bit, which is where things really go wrong. If you can stop just short of that and let things stabilize and then take a ramp at a relatively slow rate after that, that's when you bring things into normal operation. You can slow down on the wrapping, back to the proper strategies. You can bring all the chair sets up to full power. That last 10% is when you need to reintroduce stability. In the early stages, it's not such a big deal. The closer the steel temperature is to the gas temperature, the less likely you are to gum up the surfaces under almost all circumstances. It's just like driving in your car on a humid day and turning the air conditioning on. Water starts to drip on the outside of the windshield. The same scenario occurs here, except that because you've got the mills in, it creates a nice fat paste. And then you just have to look to the people that are producing cement and adding fly ash to that. And they'll tell you, and the papers that I read indicate that the thermal conductivity of fly ash is right up there with keeping things, keeping your house warm in the winter and keeping it cool in the summer. And so it prevents heat from getting to the plates. So try and monitor, try and delay as best you can. Shutdown is the same scenario because you can gum up a precipitator shutting it down just as easily as you can in starting it up. Now, I don't know what the time period that your particular plant might be shutting down over, but it's almost better to go for a really rapid shutdown than it is a slow shutdown, because the slower you go, the harder it is to get the surfaces clean. But if you can literally cease firing, and in order to cool the fans ramp up and there's no coal, you can get the surfaces clean while the temperatures are still high. Once you start to cool it down and the moisture starts to get ingrained onto the ash on the surfaces, it gets remarkably harder to get those surfaces clean again, so that when startup comes due, you can get the temperature back in. It's a bit of a chicken and egg situation. Of course, you could argue that if you keep some layer of ash on the plates, that the plates will stay warmer for longer. But it really depends on your cycling frequencies. If you're down long enough for the temperatures of the sheet metal to cool down to the ambient levels, well, that would be pretty much a waste of time. It goes on. Really, temperature maintenance is a big issue. So during a shutdown, use aggressive wrapping to clean the surfaces while the temperatures are high. Obviously, you have to balance that against the emissions. Hopefully, with the reduction in firing, you'll be producing less ash, and so you'll manage to control it. One of the big things that one should remember, and this comes, and you've probably noticed this, not even under these sets of circumstances, but when you simply turn off a TR set on a precipitator, it almost doesn't matter where it is, there's an instantaneous spike. However, if you were to power that TR set down relatively slowly, bringing it down a few kV at a time over a period of, say, 10 or 15 minutes, when you finally turn it off, there is no spike. So that brings up the point, is what happens when you physically just turn off the TR set instantaneously, you let go of all the ash instantaneously that's on the plates. And it pretty much has nowhere to go. It's back into the gas stream, re-entrain, blows off, what have you. However, if you slowly let it thin out by turning the power down and decreasing the efficiency of that field, yes, it does blow off. Yes, it does go back into the gas stream. Yes, the efficiency is not there. However, you won't see the spike. There may be a slight increase in the baseline emissions, but you won't see the spike. And if it is further towards the front, of course the back fields stand a better chance of collecting it. When you turn off the inlet field, you let go a wad of gas that creates a huge pressure drop in the system, and it moves backwards through the precipitator just like a pump, and pumps all the material that you've collected further back off the plates and back into the gas stream. So powering down during the slowdown or a shutdown or an off cycle, as opposed to simply de-energizing, not a bad way to do it.
Are our control systems usually set up to ramp down instead of a on-off?
The control in most of them is done by operators going out there and shutting them down. Okay. All of them, almost all of them that you guys have are capable, but ops don't use that methodology. When it's time to come down, they send someone out there, they turn them off and lock them out. I guess in a way it might be because you're lucky because you have the scrubbers behind, and people are only looking at what comes out the stacks as opposed to plugging up the scrubbers and what have you. But I mean, these are points that are worth considering. It's not specific to you, it's in general. During the downtime, well, again, it depends on what your cycling frequency is, but every effort should be made to keep the temperature in the precipitators. If you have hopper heaters, you should keep them energized. If you don't, probably worth putting some in, because every bit of heat that you can keep at that precip is going to help when it comes back to starting up. You should keep the wrappers running, even if you slow down the frequency of wrapping while you're down. Yes, it's true, there comes a point where they're not needed anymore. Again, frequency dependent, cycling frequency dependent. If it's short downtimes, maybe the TR sets are continuing to be run Maybe some of them are running, some of them are not running. It's worth implementing what might be called power down wrapping during that time. Remember that whilever you're energized, you are endeavoring to keep collecting ash that's floating around the system. And thin layers of ash don't fall readily when compared to thicker layers of ash. You don't get the shear. However, if you use power down wrapping, when the wrapping comes due, and even whether you have a thin layer of ash or not, you're more likely to clean. A lot of it, cycling. Temperature, re-entrainment. The only real way to do the best that a control system can do to help you through these processes is for you to do the advanced thinking so that the control system can capitalize on what you've done. If you don't have hopper heating, the hopper surfaces are going to cool. When the hopper surfaces cool, you're going to get condensation. The hopper surfaces are going to corrode. As they corrode, the next time you come back online, the ash won't slide down the surfaces as easily. And when it does, it'll be taking metal with it. If you have hopper heating and you can keep those temperatures in those hoppers up and keep the sheet metal up, you stand a much better chance of maintaining the life of the hoppers as well as getting rid of the ash when you come back online. Different plants, different manufacturers, everybody has different ways of doing things. A lot of you will have support insulators that sit in dog houses that have heater bands or insulated heaters of one form or another. Others of you will have purge air ventilation systems where you heat penthouses where the support insulators exist. Some of you will have purge air heating systems where the heaters don't work anymore and you're just purging with fresh air. I think the amount of maintenance that is required when you start to cycle really goes up because you're not faced with a continuous burn and continuous temperature. The cycling in general just causes huge changes in the temperature throughout the precipitator. Air leaks in the doors, air leaks in the hoppers. When the hoppers are empty and there's no base layer of ash above the exit system in the hoppers, air in leakage through the bottom enhances the cooling. It produces re-entrainment, so even when the plant is down, you're getting ash pushed back up into the precipitator. And the control system, of course, is trying to collect it. It's collecting effectively moist fly ash now and creating its own paste. So it all comes down to temperature. The higher you can keep the temperatures, the better insulated, the lower you can, the better you can keep the precipitator from air in leakage, the better chance you have of success and reducing the risk as you go through these cycles. These are just fun slides. Everybody's seen these hopper vibrators, and you've got to start from the clean hopper perspective. If you put a big hopper vibrator on a corroded hopper, it won't be long before it rips the sidewall of the hopper off. There's different types of vibrators, AC vibrators, DC vibrators. Some of them are great in that you can control the intensity. And then the best one is when they stop working, you big sledgehammer, strike plates and the like. All of them have their place, and people, surprisingly enough, still use sledgehammers. Okay. Wrapping, once again, is a critical issue. You really need to know where you stand in your plant when it comes to wrapping intensities and wrapping frequencies. It's very, very difficult to predict, and at least with the different utilities here, people use top wrapping, they use side wrapping. It's never that clear where the energy is going, and messing up the wrapping can be as detrimental as anything. Over wrapping, under wrapping. There's some points over here. If you wrap too frequently, you really don't get any particle agglomeration. You tend to knock ash off the plates. It doesn't have any mass as far as the larger particle sizes. and instead of going downwards, it goes outwards, and it joins re-entrained ash and heads towards the stack. So that falls into the same category as lateral releases. Even if you do have a nice, big, thick layer that might shear and you hit it too hard, you're still going to get puffing. These curves over here are pretty poor, but in essence, they show how the intensity of the wrapping spreads out across the plates. You typically get nice high intensity wrapping over here, and it gets lower and lower as it moves towards the outside. One of the great reasons for good flow distribution, but at the end of the day, most of it is from experience. It's trial and error. Keep the dust on the plates only to exactly what you need in order to minimize risk that any retained dust and moisture, when it does come time to go through the acid gas dew points, is gotten rid of, so that it can't sit there like a sponge and keep those acid gases on the surfaces. Pretty much does me for today, I believe. One thing I will say is I've listened to a lot of people speak over the years. I've read a lot of papers, and it's very rare that taking any one person's advice does a great deal more than confuse you. So I always believe it's a good idea to get a lot of advice from a lot of different people, and try and mix it together and see what fits for you specifically. There's a lot of experience, but a lot of the consultants and a lot of us designers, every time we go out, we see something new, we learn something new. However, amassing that information into a database of things that can go wrong, will go wrong, won't go wrong, and can be dealt with, is just, it reminds me of a story about a fella who came out to work on a turbine that was nitrogen cooled, and for some reason something went wrong, and he arrived on the site and he went to look at the job, and he pulled out a small hammer. He went over to one of the valves and tapped on the valve and walked away, and he sent the company a bill for $10,000. And they said, $10,000? Are you out of your mind? You were there for 15 minutes. So he wrote back, okay, here's your new bill. $9,500, knowing where to tap. $500 expenses. So it comes down to that. Any questions? Yes, sir.
So how thick of an ash layer do you have to build up for it to drop off like it should?
No answer. Depends on the particle size, moisture content, the resistivity of the fly ash, the chemical makeup of the layer.
What's the range of this?
It's really hard to say. If you have a relatively low resistivity fly ash, it literally comes off by itself. If you have high acid gas content, same thing, that brings the resistivity of the fly ash down, and so it'll fall easily. With the higher acid gas content or the higher moisture content, the agglomeration is better, so the mass of the individual clumps is better. So you can get quite a good shear at thicknesses less than an inch. Some of the places you'd think that maybe we would get better shear with larger buildups, but the reality of it is such that the energy reduces the underlayer, and so it falls down on an underlayer basis because the outer layer is still being attracted to the plate. The inner layer is not, because of the dielectric strength of the material and the voltage drop across it. So the inner layer takes the gravitational energy from the wrapper and moves down, but the outer layer gets stuck again. So there's no one rule. We did some tests a long time ago where we put weight measuring instruments on the plates, and we tried to measure the weight of the plate before and after a wrap in order to determine at what point the best mass of the entire plate system might be in order to wrap. It was so diverse you couldn't draw any conclusions. It really depended what part of the process you were in.
What experience have you had with, obviously, high resistivity ash is problematic in terms of collection. Have you had any experience with controlled humidification in front of the inlet to reduce that humidification, or that resistivity?
Yeah, and it's all been bad. The controlled humidification aspect. I have to tell you, I don't want to take any responsibility for this, but every time I've seen somebody do a controlled humidification injection system, the actual humidification process has been a disaster. It hasn't given the precipitator a chance. The ones that I've seen, they inject the moisture, the nozzles are in the wrong place, the moisture particle sizes are wrong. It hasn't even got to the point where we can draw a conclusion as to whether the resistivity modification has been good or not.
So it's been poor design of the humidification system.
I think that's a fair statement. I personally believe it's a great idea, and there was a company many years ago that purported to have been successful, and I think it was EnviroCare built a humidification system for Jim Bridger, right? Is that right? And they purported that to be successful. But the ones that I've seen since then, the water's ended up coming out the hoppers. It's just not been, it's not, the precipitator hasn't had a chance to work with the modification process. Now the flue gas additive side of it, of course, that's been tremendous for us. It makes our job that much easier. But straightforward moisture and steam, no. On the cement plants, of course, it's different. You know, in the quenches and the coolers up ahead, and the temperature reduction there, it's great. Without those, some of them don't stand a chance. But that's not so much of a moisture injection system in the inlet to the precipitators.
So having a good distribution with the proper atomization at a distance far enough away from the inlet would give it a better chance.
If your temperatures are high enough, I believe so. But nobody seems to be able to get that part right. So until you get that part right, I'm not sure where you would go with that information.
Okay. And the other thing is that you talked a lot about the cycling as part of this, and the problems that it sounded like you were referring to in cycling as coming offline and then coming back in a short period of time, as opposed to coming down to minimum load.
In the case of a lot of places, minimum load is, what they keep the unit running at. Some places come down completely and some places don't. It all depends on the frequency of your cycling and your demand.
Right.
Personally, I hate it all. The sheer fact that you have to continually change the load on the precipitator does no favors to anybody. Sheet steel and temperature is a very slow process. I mean, just look at any heat treatment process. Temperatures don't change instantaneously. You have to wait for them. And we don't have anywhere near the heating capability of a heat treatment system.
Yeah.
We're stuck on gas and huge volumes of material. So we can't get those temperatures.
I'm just thinking in terms of the way in which the normal operation for what your minimum load is often dictated by what it characterizes as minimum operating temperature, which is a function of the.
But that's of the boiler. That's of the front end. The minimum operating temperature on the precipitator is dependent on the air heaters, all the holes in the precip, the leakage in the hoppers, the stuff that comes back up through the ash handling system. And you can be higher in temperature at that end and still be sucking in all this moist, damp air down at the other end. So again, it's not a straightforward answer.
Okay.
I mean, I'd like to think it was, and I'd like to think it was all perfectly sealed and there was no stray air coming in. Yeah, if only, right? What's that mean? You've had enough and you want to
It's
cut
the
the flow?
hook. It's the hook.
Any more questions? Who has precipitators here? Oh, great. Who has bag houses? Well, thanks for coming.
Well,